is Dr. David Laverty from Queen's University Belfast. Is my former colleague. His presentation today, as you can see from the screen, is about the open source measurement technologies for electrical distribution network. David was born in Belfast, Northern Ireland, and he is educated all at Queen's University in Belfast, and he's currently a senior lecturer with the Energy, Power and Intelligent Control at Queen's, and I think he's spent the most time in Northern Ireland. So his research is on the anti-aliasing detection and telecommunication, cybersecurity, and synchrophase measurement. Particularly, David, he's the founder of the open source phase measurement unit project, OpenPMU, and which is actually being used in UK and Ireland, but also a few other countries. So today he's going to share his experiences and research in this area. So let's welcome David.
Thank you very much, Professor Lee. Okay, so my presentation today on open source measurement technologies for electrical distribution networks. I guess the first question is, why on earth is there any sort of issue in terms of measurement technologies for the electrical distribution networks? The thing is, do we not already have information from the network? Well, for a start, we have the obvious one. You know, we measure energy that consumers are using through today all sorts of modern electronic instruments and smart meters. And through these smart meters, we're told that we can access additional information such as high resolution power measurements, although people's opinion of what constitutes high resolution varies considerably. Realistically, a lot of utilities only update their measurements from these at most once every 15 minutes. In practice, usually at a much greater interval than even that. But we're told that the meters can also measure voltage magnitude, frequency, and look out for power quality issues. Is this sufficient? Well, first of all, let's consider the topology of the distribution network. And it's important to consider that the topology of distribution networks does vary country by country. Superficially, we can say that there's two main types of distribution network. On the left-hand side of the screen, we have an example of what's representative of a distribution network in North America, where the high voltage from the transmission network is stepped down to medium voltage, and that medium voltage is brought very close to the consumer premises, where then it's stepped down to supply voltage by a low voltage transformer adjacent to the property. And you would often see a small number of houses numbered 2 or 3, or at most maybe 4 houses on a distribution transformer. Conversely, in networks across much of the rest of the world, and as is true in the UK and across Europe, we take a different approach, which is that the transmission voltage step down to medium voltage, and then large transformers step that down to supply voltage, and we feed a great many houses from those supply transformers. In fact, it's quite common on distribution networks in the UK. You could easily have 100 homes connected to the low voltage side of the transformer. And of course, then there's also the quirks of how in much of the world on 230-volt systems, households will be supplied with single phase, and in North America you have the split phase arrangement and all sorts of complexities arising in terms of measurements there. So whenever we're reviewing any literature on this, it's important to remember that there is no one-size-fits-all solution to measuring the distribution network. The topology of distribution networks varies on a macro level between countries, but also it varies within countries depending on, is it an urban environment, is it suburban, is it rural, etc. There's all sorts of aspects we need to take into account. So what we're trying to get towards, as we've heard, the smart grids, obviously, we want to have consumer participation, the integration of renewable energy. Effectively, we're trying to get to the point where our devices can participate in markets. Obviously, our applications we're trying to achieve are reliability, self-optimization. We want improvements to power quality, etc. And we have to do all of this in the context of cybersecurity. Effectively, what we really want is to have information on the state of the distribution network similar to what we have at the transmission system. At the transmission system, we've become accustomed to having SCADA measurements updating at about 10-second intervals, and phaser measurement units are introducing the possibility of getting updates on the state of the system on a per cycle basis. Basically a new measurement once every 20 milliseconds, or 16 2/3 of a second on a 60 hertz system. So can we do that in the distribution network? And indeed, do we want to do that in the distribution network? Do we want to have such high resolution measurements? Before we delve into that question, let's take a look at the phaser measurement unit, the tool that is very often described as the go-to measurement technology of the smart grid. So typical transmission system phaser measurement unit is a big 19-inch rack box which bolts into a panel in a substation. What does it do? So phaser measurement units represent AC waveforms. They turn AC waveforms into phasers. So phaser representation in AC power systems, of course, can trace a lot of its mathematical roots to Charles Steinmetz in the late 19th century. One important thing that we should note is that it's very often said in literature that Steinmetz created the modern representation of a phaser. He didn't quite. He set out the mathematical description of a phaser, but the way that he drew his phaser diagrams, we wouldn't really recognize. They came later. But regardless of that, the point is that phaser representation greatly simplifies the mathematical complexity of analyzing AC systems. They're a fantastic tool. They reduce the information that we have to deal with from the time varying AC waveform to basically scalar value, well, obviously vector values, but they reduce magnitude to scalar value, phase angle to scalar value, etc. So we can now just apply vector maths to the problems, and that greatly simplifies our modeling and planning of power systems. An important point, though, is that a phaser describes amplitude and phase angle of a time invariant waveform. So what use are they whenever we're dealing with systems that are experiencing faults? Because a fault is obviously a very time variant issue. Well, strictly speaking, phasers are only valid whenever the frequency of the AC power system is constant and is the same throughout the whole system. That's an issue at transmission networks, but again, it's something that actually we have a little bit of a benefit in terms of the distribution network. Because sections of distribution network are so small, we don't tend to see phase oscillations across them. It would be very unusual to end up in such a situation. So a typical phaser measurement unit is constructed as so. This is taken from the book by Thorke and Karimi, published in the mid-1980s. Sorry, it's the paper published in the mid-1980s. Their book followed later. But their paper sets out that a phaser measurement unit basically has three components that process information. The first stage is an analog to digital converter, data acquisition stage, which takes our analog voltage and current quantities and it turns them into symbolic representation. It turns them into sampled values, which we usually express in our computer as a binary value. We then have a signal processing stage. That signal processing stage applies some mathematical model to the sampled values, and from that we'll estimate the magnitude of our phaser and the angle of our phaser. as well as usually additional parameters such as the frequency, rate of change of frequency, and so on. But essentially our phasor has a magnitude and an angle. It is a vector after all. And those estimated quantities are then sent off to the final block, which packages it up into a data schema, which allows other applications to interpret and understand what the phasor looks like. Crucially, this whole process is disciplined by a time source receiver, very often using GPS. In fact, almost exclusively in my experience, PMUs will use GPS as their time source. And the benefit of that is that our synchrophasors are now disciplined to a common time signal across the entire grid, and we can usefully compare phasors taken at different points across the grid. Now, as was mentioned, I founded the open source PMU project called OpenPMU. And what was the motivation to do that? Well, back whenever I was doing my PhD, as Kang mentioned, I have spent my entire education at Queen's University, Belfast. We were trying to investigate problems around the protection of embedded generators, particularly the whole issue of loss of mains detection. And we had some pre-existing work in this which suggested that synchrophasors was a viable route to follow. However, whenever I started to investigate the quality of the phasor measurement units, several commercial off-the-shelf phasor measurement units that we had, well, it quickly became apparent that not only were these things needlessly complex to configure, considering what the devices do, they were extremely unreliable. These were expensive pieces of equipment that we had purchased, and there were some absolute beginner's mistakes in the electronics in them, the sort of mistakes that you wouldn't expect a competent radio amateur to have made. And as I mentioned, they were exceedingly expensive. So basically, after some investigation of the hardware of these things, it quickly became apparent that there was no possibility of fixing these. But more importantly than any of that, remember, I was a PhD student, I was concerned about writing my thesis. These were mystery boxes. These were a box that, you put AC quantities in one end and a phasor came out the other. What was it doing internally? I couldn't get any description of the algorithms that these boxes were operating, because the equipment vendors considered this to be their secret recipe, and that it was a trade secret, and obviously they couldn't tell me what it was. This seems an absolute nonsense for a measurement instrument. What use is a measurement instrument to anybody if they don't know what the measurement algorithm is? So I was very much motivated from the point of view of producing something that was academically defendable, to have a PMU in which the guts of it were visible and open for anybody to investigate, and anybody could see how this device worked. So in my OpenPMU project, we've created a device which you can observe from the very beginning, from the terminals at which you apply your AC quantities. You can see the analog stage and you can understand the analog circuitry. You can see the exact analog to digital converter we're using and how it's configured. The software algorithms are open source. The communication stack is open source. So the entire device is totally transparent for anybody who's interested in it. And a happy consequence of this is that because we were using commodity hardware to do this, it became very low cost. So OpenPMU is built to the same concept as what Thorpe, Fadke and Karimi outlined in their 1985 paper, in that it has three distinct blocks. It's been built on a modular design. So the voltages and currents go into the measurement block, which is the analog to digital converter. The sampled values are processed by a mathematical algorithm, a software algorithm, which turns to a phasor. And then there's a telecommunications block, which handles onward communication to the outside world. As mentioned a few slides ago, this all needs to be disciplined to a time source receiver. So this is where we do our time sync. We do our time sync at the measurement stage. At the moment we acquire the sampled values, we know when our sampled values are taken to a resolution of about 50 nanoseconds. And because we've done that and we time code the sampled values, everything else in the process can become asynchronous. So the whole system is the OpenPMU. The first bit is a hard real-time function. Basically, we have to make sure that the measurement process, the point at which we acquire the sampled values, is done in a way that's rigorous, that our clocks are all working like clockwork, and the sampled values are all very, very much disciplined, and we know the time of each sampled value. The rest of it, as I mentioned, is asynchronous. All you need to do there is to have a fast computer that can keep up with the sampled values that are being thrown into the pipeline. And we'll look at the types of devices that manage to achieve that in a moment. Oh, I have a problem with my animation. There we go. So the core of a phasor measurement unit is that which I've outlined at the top here with the green dashed line. That is a phasor measurement unit, or in my case, in this slide, that is the OpenPMU. Very often, phasor measurement units are multifunction devices and will do other stuff. For instance, they can have transient detection and capture the sampled values. That is the function of a disturbance fault recorder. That's not a PMU's function. But obviously, it's very easy whenever you're dealing with software to create additional modules and bolt on additional functionality. So within this modular design, of course, you can do that. But it's just an important clarification to make that the green dashed line is the function of a phasor measurement unit, and things which exist outside of that are additional functionality or aspects of a multifunction device. So as promised, the hardware looks something like this. The device we use to do our hard real-time function is a BeagleBone Black. And the benefit of this is that whilst it has a fast ARM CPU that can run a Linux operating system, it also has two companion processors on the same silicon die, which can be programmed up with a very small program and operated in a hard real-time function. In fact, they call these the programmable real-time units. And because these programmable real-time units share memory space with the Linux host operating system, these small co-processors running assembly in our case, and one of them has a little bit of C++ in it, those functions can control the analog to digital converter, which sits on a little daughter board, and can pipeline the sampled values from that analog to digital converter at known instances in time into a shared memory buffer, and the Linux host OS can then start processing that asynchronously and pipeline that data off to the rest of the functions. And in our case, whenever we talk about needing a fast computer, well, remember that the origins of OpenPMU started about 12 years ago. At this stage, a fast computer used to be something with an Intel processor in it, but the developments in single board computers now mean that a fast computer is a Raspberry Pi. So in this system, we have a pipeline where we pipeline the data in XML datagrams, as in we've formatted the data in a nice human readable schema. And the advantage of this is that it's very easy for somebody to come along and to inspect the data that is flowing through the pipeline. You know, you can very easily in virtually any software environment, we program almost all of OpenPMU in Python, but you know, you can use MATLAB, LabVIEW. There are interfaces that exist for DIG silent, so you can take simulated sampled values and pipeline them through a real PMU, so to speak. It makes accessibility of the data very convenient to non-expert programmers. Basically, if you have some background in MATLAB, you'll find it trivial to be able to access the raw data out of the OpenPMU system. So that in a nutshell is OpenPMU. What are some of the challenges which exist in terms of measuring the distribution network? Well, as I alluded to, one of the big problems that we have is that synchrophasors only describe AC waveforms. That is, that the waveform must be continuous, it must be time invariant. Strictly speaking, the mathematical definition says that it must be totally time invariant from t equals minus infinity to t equals plus infinity. So in this case, we have here on the left-hand side of our screen a snapshot of the oscillography of the sampled values that are being pipelined into the system. And our mathematical model for the phasor estimator, taken from the IEEE standard, is telling us that we want to fit our phasor to these sampled values such that a sample xt is equal to a magnitude times cosine 2 pi ft plus phi. So with 3 degrees of freedom in this, we have the magnitude xm, we have the frequency f, and we have the phase angle phi. Now, whenever we have a time invariant waveform, we can do that quite well. And on this diagram, we've shown the estimated phasor as dotted lines superimposed on top of the solid lines, which are the sampled values that were required. On the right-hand side of the screen, we have a problem. On the right-hand side of the screen, we have sampled values coming into our system, which are very clearly not time invariant. There's something going on. So up until about 0.14 seconds into this oscillograph, everything looks okay, but then there's some sort of an event. The magnitude of our blue signal has become suppressed, and there's a DC offset has occurred, and one would say there's probably even a phase step. So this is really a perfect storm as far as a phasor measurement unit is concerned of an unsolvable problem. And as a result, our phasor estimator has tried with the degrees of freedom that it has available to it to solve for this, but it can't. And we can see here that the dashed blue line, which represents the estimated phasor, it doesn't really fit the sampled values that went into the phasor measurement unit. So this is something that I would urge a lot of caution on, that there is so much in the way of literature at the moment discussing the use of phasor measurement units to study faults on power systems, both at transmission level and at distribution level. But are phasor measurement units useful for understanding faults? Maybe leading up to the fault, maybe in the aftermath of the fault, but one would argue that not necessarily during. Now, some other challenges that I could spend a lot of time going through, and I'm happy to bring up in the discussion if it's desirable, but we have other challenges such as frequency measurement. There are at least 50 definitions of how we should measure frequency, and I think there's about 7 common ones that are used. Problem is, if all of our various instruments being installed in the distribution network are using different definitions or different methodologies for estimating frequency, how do we usefully compare them? Likewise, with reactive power, we have many definitions in the wild of reactive power. That is, there are many definitions set out in standards for reactive power, and consequently different instruments use different approaches to estimating reactive power. And likewise, the various power quality measurements that exist. So one of the big advantages of having an open source toolkit such as OpenPMU is that, again, you can create open source measurement algorithms for frequency measurement, for measurement or estimation of reactive power. And this very much fits into the OpenPMU ecosystem. Now, by doing so, by creating, say, a frequency measurement algorithm, it's no longer an open source PMU, it's an open source frequency meter, but it can use the same tool chain, just as OpenPMU has described. So it affords us a great opportunity in terms of distribution network measurements to do something new. One point to stress is that there are issues in terms of hardware. Whilst OpenPMU has been developed as a research project within Queen's University, and we've had lots of international collaboration, in terms of developing that. We are okay using the PMU in the context of research projects, where we have the university's insurance to underwrite us if anything were to go wrong. But broadly, we have a challenge that this hardware is not certified for use. It's basically homebrew hardware that is being made in our research labs. So the next critical barrier, or the quantum leap in progress, which this technology will need to overcome, is to have a certified piece of hardware to do the sampling process for us, to capture the analog values. And that is something that I'm very keen to explore with any collaborators. You know, how will we get this device to be certified to meet the various IEC standards, the UL standards and test requirements for this to be used in many jurisdictions across the world. Anyway, I think I'm approaching my time limit, so I'm going to wrap up at this stage. Thank you very much. I appreciate this has been a tremendous whirlwind course, and realistically, I've only touched superficially upon the challenges in distribution networks. The real issue that we have is that the distribution network is very far from the sinusoidal world that we're used to at the transmission system. And consequently, our models for our measurement systems, we have to treat very cautiously. So that being said, I'll wrap up at this stage. And as I say, very happy to take any questions now or subsequently. Please do feel free to reach out to me by email.
Thanks very much, David, for presenting your fabulous work on the development of OpenPMU. Obviously, to apply the OpenPMU to the distributed network present a lot of challenges.